So my name is Vincent van Eylen, and I'm a PhD student in Aarhus University at the Stellar Astrophysics Center, and I will talk about Kepler 410. The work has been published in the Astrophysical Journal recently. Together with a lot of people, I'll just explicitly mention Miguel Lund, a fellow PhD student in Aarhus, and my advisors Simon Albrecht and Hans Kelsen, who is conveniently chairing the session, so he's promised me I can talk for at least an hour. And so my subtitle is What Asteroseismology Can Do for Exoplanets. And I thought since we're in France, I would pick a theme that's at least somewhat French. So you might know the book by Jules Verne, Le Tour du Monde en 80 jours. For the more English-speaking people in the audience, around the world in 80 days. And so I've took my best Photoshop skills, and we've changed this into how to find a planet in 15 minutes. Now, before you stop listening, you might ask, we already know 2,000 planets, why do we even want to find one more? And I should say this is a question that only really comes up in an audience of astronomers, because non-astronomers don't seem to wonder why we would be interested in finding planets. They always are. But for me, for astronomers, I think there are two good reasons why we are still interested in finding planets. One would be that there are some systems that are particularly interesting. And that might depend on your preference. They could be habitable zone planets or multi-planet systems or whatever you're interested in, and those are typically the ones that are actually the most difficult to find and the ones we have very few of. The second good reason why we could be interested in doing that is that some systems are what I call benchmark systems. Those are the systems that we will know very well, that we will get detailed properties of, or properties we can't even get for any of the other systems. The kind of planets that will show up with low error bars on those distribution plots. And so that's typically around bright stars, with good stellar parameters, and for what I will talk about now, eccentricities and obliquities. And so my new title is How to Find a Particularly Interesting Planet and Learn Everything, and maybe I should have added almost everything, about it in 15 minutes. And so we do that with a planetary transit. So you probably know this figure, so planets move in front of a star, and we have an instrument for doing that. Kepler measures time series. And so step one in finding a planet is to have a planetary candidate, and we pick KOI 42 here. So you see a beautiful transit. You should notice the y-axis here. This is really a transit only 200 ppm deep, and there is really no doubt how this looks like a planetary transit. And red is the model, and then you have residuals. And I should add, this is KOI 42 is magnitude 9.4, and for people who work on Kepler, this really is almost the brightest case that we have. So this is a small planet in a 17-day period. There's one other interesting thing about it. There are transit timing variations, which are shown here in this O-C diagram. So there is deviation from the linear ephemeris, indicating that there is at least one more non-transiting planet. So we're actually dealing with a multi-planet system. And I should say that KOI 42, the number sort of gives it away. It's number 42. It's one of the first that was detected. Yet only now we've actually validated the system, because the validation, step 2, is actually quite complicated. So this is, of course, what we're hoping to see. We're hoping to see a transiting planet causing that transit that we've just seen. But what we could also be seeing is a binary star blend. So we're observing all this together. And so a binary star in the background causes a deep transit, but is heavily diluted by the foreground object and causes the shallow transit we see. And then we have a binary star in the background rather than a transiting planet in the foreground. And so to rule out that scenario, I'm going to build up this figure. And so we have here our star in this corner, and then this is distance. So we go away from our star in arcseconds, and this is delta magnitude, so we go towards fainter objects. So this is magnitude 9.4, and then we go fainter. And so ideally, we would like to say that there is nothing in this entire plot that can cause any confusion. So this is where we hope to be here. We have a transiting planet. And this is very diluted, where we really don't want to be. Now, the thing to notice is that as we go to more diluted objects that are intrinsically deeper transits, the transit shape also changes, because those objects are more and more equal sized. And so we get more and more V-shaped transits. And if you remember, in the case of KOI 42 here, the transit really does look like this and not like this. So we can set a limit, and actually about 3 magnitudes fainter than our true objects, we can rule that out as not being able to represent the shape that we've observed. So we still have this region up here, and there is some ground-based observations by these authors with spectral imaging and adaptive optics who've actually measured this area, and they do not, they cover much more than Kepler can do. But they do find a second star. And now this is really interesting, because now we have a binary star system. But it's really annoying for planetary people, because now we really have two scenarios. We have a scenario AB, where we have our planet where we would like it to be, or we have a scenario BB, where we have a bigger planet. It would still be a planet, but a bigger planet on this fainter star. This star contributes about 10% of the light. And so in Kepler, that would dilute to exactly the same transit, and so we cannot really make the difference between those two scenarios. However, as you see here, this is a red star and this is a yellow star, so the stellar properties are different. And so if we would go to the infrared, this fainter star would actually contribute relatively more light. Instead of 10% of the light, it would contribute 20% of the light in the infrared. So if we turn to Spitzer, at 4.5 micrometer, if we're in scenario BB, the dilution would be far less, about half. The transit would get twice as deep. In the other case, the transit would get a little bit shallower. And you're going to guess what's on my next slide. We have Spitzer observations, and they were observed for quite a number of systems. PI for this program was Dave Charbonneau. The data's still there. There's actually quite a bit of Spitzer data still there. It's remarkably difficult to analyze. You see the scatter here, the original data points, and blue is the bin data points. You might not think this is gray transit, and it is not. But this is our 1 sigma error bar here, this gray box. And this matches with red, which was our scenario AB, and not with blue, which was our scenario BB. So from this, we can rule out our planet on the fainter star, and we actually have now found the planet. This is an artist an artist impression. And so we have our star here, and a beautiful planet here. You can kind of see palm trees, alien camps, and all that, sugar fields. And so this is the orbit to scale. And I couldn't resist showing this. This is the Twitter account of the Belgian Prime Minister. You can see him here, Elio Di Rupo, and he says, "Congratulations to the Belgian Vincent van Eylen, who has discovered a new extrasolar planet. Hashtag Belgian talent." That is a reason to find a planet. But of course, I promised the astronomers in the audience more. I promised we would actually learn something about it. And so what we can do for that is use seismology. And the first thing to notice is we can get stellar parameters. So this is a power spectrum. This is a Fourier transformation of the Kepler time series. So you see frequency versus power, and you see this regular pattern here of frequencies. We compare them to stellar models, and we get stellar parameters out. Values here are a little bit larger than the sun in mass and radius, but really this is percentage level accuracy, which is truly quite amazing. Also an H here of 2.7 gigayear. As Victor said, I would also talk a little bit about eccentricities. So why is this interesting? Well, with radial velocity measurements, we can routinely measure eccentricities of planets because we measure the full orbit. However, for small planets, we cannot actually measure radial velocities. If they transit, we see the transit, but the transit is only a small part of the orbit, so we don't see the rest of the orbit, so we don't measure the eccentricities. However, Kepler's law, and I've shown it here, does give you some hint of how you could do it, because some parts of the eccentric orbits are traveled faster than others. And so from the duration of the transit, we can actually measure something about eccentricity anyway, even if we don't see the rest of the orbit. And so how this works, this is pretty much high school mathematics. This is Kepler's law. So you have period squared is equal to A to the third power, that's the semi-major axis, divided by the total mass of the system, and then some constants. We remove the planetary mass because the stellar mass is much larger, and we have this equation. And now we divide both sides by the volume of the star. So what we have is stellar density is almost equal to this property here. Now, for a circular orbit, actually A over our star is a directly observable property that you can directly get from the transit duration. And of course, this period we also know. So it actually means that we can derive the stellar density from measuring a transit. And this fact was realized more than 10 years ago by Sarah Seeger and collaborator. But we can also turn this around, and we can say if we do know the stellar density already, we can now say we know what A over our star should be, and from measuring the transit duration, we can see, is this truly a circular orbit? And so this fact has also been realized by several people and has been done in a few cases. And the key thing to notice here is that asteroseismology really does provide a very good measurement of the stellar density, which we can use to compare with the transit duration to get the eccentricity out. And so this is our posterior distribution. You can see that they don't exactly match, so a circular orbit is excluded. High eccentricity orbits are also highly unlikely, and so what we get is an eccentricity value with this kind of error bar. So for long period planets, it is possible to measure eccentricities of the orbits, even if you can only see the transit. And so my third point, what we can do with asteroseismology, and maybe arguably the most interesting one of this system, is to measure the stellar obliquity. And so hot Jupiters, they display a wide range of obliquities, as we've now seen. I do not show the figure again. The question is, what's the cause for this? Is this planetary migration? And some people have suggested there is a primordial misalignment of the star and the disk. And so one way out, one additional observation that would constrain those scenarios would be to observe the obliquity in multi-planet systems, where we could then compare the more than one planet with the stellar inclination angle. The only problem is that these measurements for hot Jupiters use the Rosetto-McLaughlin effect, which is a radial velocity anomaly during the transit, and they're not possible for small systems to do. So for small systems, we really can't do that. Luckily, we can use rotational splitting. Thanks to Victor, I don't have to show this movie again. So we split modes in M-1, 0, and 1, and we get rotation rates and inclinations out. And I'll just show you the results. So this is our power spectrum again. We can now zoom in on two of the frequencies here. And so this is how that looks. And so this is an L1 mode. And it actually splits into three components, the -1, the 0 here, and the 1 component. And the thing to notice is that the 0 component does not really show up very much. And that is consistent with an inclination close to 90 degrees, close to seeing the equator. And so to guide your eye, we've put up a model here of 45 degrees. That would mean that the 0 mode would show up much clearer, and that's not what our data shows. And so this has been seen in quite a few L1 modes. There's more in the power spectrum. And also in the L2 modes, which splits in 5, you can see the same effect. And so as a consequence, we really find that the inclination is very close to 90. And this is the posterior of the MCMC distribution. So this is all those measurements, and then you get out two things. Here you get out the rotation, it's about 5 days. And here you get out the inclination angle, close to 90 degrees. So do multi-planet systems have a low obliquity? Well, for Kepler 410, KY32 now changed to Kepler 410, we get an angle close to 90 degrees. There's been measurements on Kepler 50 and 65, again consistent with 90 degrees. Slightly higher error bars because systems are slightly fainter by Bill Chaplin last year. There's been some other measurements from spot crossings, which means that transit crosses over a spot, and from that the relative inclination has been measured. Now low numbers, this is an obliquity measurement, so now low numbers again mean alignment. And finally, there's been two Rosetto-McLaughlin measurements on KY94 and Kepler 25, again consistent with low obliquity. And so I think Otman will talk a little bit more about Kepler 25, but all those systems, 7 now, they are consistent with having a low obliquity and aligned system. However, there are two exceptions to the case so far. Kepler 56 by Dan Huber last year is misaligned. 55 Cancri-E very recently, also with the Rosetto-McLaughlin measurement, also appears to be misaligned. And so with that, I will come to my conclusions. I said we would try to find two really interesting planets. So this was a candidate that has been known for years, but we finally validated it. It was not easy. We had to invoke a lot of other data, such as Spitzer data, but it can be worth it. It's actually the third brightest Kepler planet host now. It's a multi-planet system with non-transiting planets from TTVs. And then I added to it almost here now. We do get precise stellar parameters, and those give precise planetary parameters. We get a stellar density, which gives the eccentricity of the planet, and we get the stellar inclination from seismology, which gives the obliquity. I did stick to my 50 minutes. Thank you.
Thanks a lot, Vincent. Questions, comments? Jan?
What are the constraints on the non-transiting planets seen in the CTV? Do we know anything about that, except that it's there?
That was outside the scope of our measurement. TTVs are notoriously difficult, particularly if they are not transiting planets. Since the paper has been published, several people have asked me for the transit times to look at the TTVs. So far, I'm not sure how far they've gotten. So we don't know very much. It doesn't have to be very far misaligned, though, to not be transiting. If it's in an orbit that's 30 days, it would only have to be 1 or 2 degrees off to not be transiting anymore. So that there's no issue there. But we don't really know very much about the second planet.
Other questions? Yeah.
I just have a general question about using seismology, the visibility. of the modes to infer the inclination of the swing axis. For you and for previous speaker, the underlying assumption is that all these modes, m equals 1, m equals 0, m equals -1, have intrinsic amplitude. This may be okay, but I was reminded yesterday in, I think, Don Kurtz's talk, the modes he had, if I remember correctly, there's a possibility that the intrinsic mode amplitude in his case is maybe very different.
Sure. So,
right? So this is a general question, how valid this is.
So I should have maybe made this more clear, but so the thing to notice is that this power spectrum here, this is a solar-like oscillations. These are P modes, regularly spaced, main sequence star, and they behave much more regularly than the kind of stars that Don works on. So I don't think this is an issue for these kind of stars.
First here and then Jan.
Yeah, can you please go back to the slide where you show Spitzer data?
Yes.
Maybe I'm a bit biased by the Kepler data, but it looks like there is pretty much scatter in this plot, and I'm afraid that your signal, which you see in the beam data, will strongly depend on the beam width that you choose. Did you check that?
Yes. I can understand your concern about the Spitzer data. It maybe is an example for how spoiled we are with using Kepler data. So yes, there is a high scatter here, and I did try a lot of different bindings, and they consistently result in measurements somewhere here. The other thing is that we knew exactly when those Spitzer data had to be taken. We knew exactly when the transit would happen, and we do see a dip no matter how you bind the data. And there is no way I can bind the data to make that dip be exactly at this blue line, which is much deeper. This blue line actually is much too deep for whatever the scatter is. So there really is no way to get towards scenario BB here. You might not believe the exact depth here, but it is always somewhere in this region, and it's never in this very deep region, which would be the other scenario. So I wouldn't try to use this as an atmosphere measurement of the planet, but to rule out the other system, I'm confident it does work.
Jan?
I just want to get back to the problem of the amplitudes, which is important for this technique to work. And the point here is that we are talking about stochastically excited modes, where the amplitude is determined by the balance between the energy input from the stochastic turbulence and the damping. And that, on average, is independent of the azimuthal order of the modes. So if you observe for long enough, many lifetimes of the modes, then you expect that, on average, the amplitude should be, the real amplitude should be the same, independent of m. And therefore, what you see only depends on the inclination angle. Well, the lifetime of these modes in main sequence stars is 5–10 days, and we're observing for years. So we're long enough.
Final from Jesper, and then we move on.
Oh, it's just on the same subject. I just warned that the other issue is what the sensitivity of observing the mode is to position on the star. To do this, you have to assume it's axisymmetric. So it's a simple limb darkening. If it's not, then these measurements don't work either, like big spots at poles or oblateness because gravity darkening, or if you're doing velocity observations and you have a moderate V sin I, it doesn't work.
Yeah, so I take your point. Again, I think for certain kind of stars, it's very difficult to do. But for these main sequence stars that are very similar to the Sun, I'm much less concerned.
Let's thank Vincent again.